Hello and welcome back. So in this video I'm just going to be looking at a spider diagram of the organic reactions that we've studied so far this year. I've been very impressed with some of the spider diagrams that I've been looking at on GOL, so thank you very much for those. Many of you have included extra bits of information, which is great, but I'm just going to do a very basic and standard spider diagram. I'm not going to be covering any of the amines or the amide reactions because you haven't studied the nitrogen organic chemistry yet, but I am going to be going through all the reactions that you've studied so far this year. Okay, so we're going to start with one of the first functional groups you looked at right back in December of last year, and that's the alkanes. So the alkanes. And the next one you studied was the alkenes. Okay, and you can turn an alkene into an alkane by adding hydrogen and a nickel catalyst at 150 degrees Celsius. I can turn both of these into halogenoalkanes. Okay, I can do that for an alkane by just using a halogen, and I'm going to use X to stand for my halogen, and this now needs to be done under UV light. An alkene, on the other hand, can be turned into a halogenoalkane by adding a hydrogen halide. If I wanted a dihalogenalkane, I would just need to use bromine or chlorine or something like that. The halogenoalkanes is a new topic that we've been studying, and there's quite a lot of different chemistry I can do with this. So, starting off on this side, I can turn it into an amine, and I can do that by adding ammonia and heat in a sealed tube, and that has to be dissolved in ethanol. And that's heat in a sealed tube. It's quite a funny thing, but you heat it in a sealed tube. Okay. What else can I do with the halogenoalkanes? Well, I can turn them, and I'm going to come right down the page for this one. I can turn them into what's called a nitrile. And for this one, I'm just going to add KCN, potassium cyanide, again in ethanol. I can turn them into alcohols, and I add sodium hydroxide or potassium hydroxide, this time dissolved in water, and I'll get the alcohols. Now, depending on the halogenoalkane I start with, I could get a primary alcohol, I could get a secondary alcohol, or I could get a tertiary alcohol. Now, I said we had to be careful of the solvent, because in ethanol we get some things with water or aqueous, we get different products. Because we can use the same reagent, we can use potassium or sodium hydroxide. If we dissolve it then in ethanol, instead of getting the alcohol, we can turn it back into an alkene. So I can have again hydroxide, but this time in ethanol. So that's that reaction there. Okay. The alcohols, we've studied them as well this year, and again there's lots of different reactions we can do with them. So the alcohols and the alkenes are linked. I can turn an alkene into an alcohol by adding steam and concentrated phosphoric acid, H3PO4. This is one of these weird ones, because if I want to turn the alcohol back into the alkene, I just need to add the same H3PO4, but no steam. So that reaction can go either way. Okay, with steam I can turn the alkene into the alcohol, and going the other way I just need concentrated phosphoric acid. I can turn any of these alcohols back into a halogenoalkane. Obviously there's different halogens, so I've got different reactions. If I want a chloro, I'm going to use PCl5. If I want a bromo, I'm going to use sodium bromide and 50% conc H2SO4, sulfuric acid. And if I want the iodide, I'm going to use iodine and red phosphorus. Okay, so that's that first part done. So the alcohols, they also have a range of reactions. I can turn an alcohol into an aldehyde, and I can turn that aldehyde into a carboxylic acid. This is all oxidation, and the reagents are potassium dichromate, K2Cr2O7, and sulfuric acid. Now, if I want the aldehyde, I have to distill off as soon as it's formed. If I want the carboxylic acid, I'm just going to heat under reflux. Secondary alcohols can be oxidized to ketones using the same reagents, and tertiary alcohols can't be oxidized under normal conditions. Okay. The other thing I can do is I can go backwards, because if it's oxidation going forwards, it's reduction going backwards. So I can reduce my carboxylic acid using lithium aluminium hydride, LiAlH4, in dry ether. I can also reduce the ketone to the secondary alcohol using exactly the same reagents. Okay. Carboxylic acid is the new functional groups we've been looking at, and there are several things that I can do with this. I can turn it into an ester. Put that up the page, ester, by adding an alcohol and concentrated sulfuric acid. This reaction is actually reversible, so you're going to come back the other way as well. Okay. The next thing I can do with the carboxylic acid is I can turn it into an acyl chloride. That's one of the new ones you've looked at, and that's with PCl5. If I want to take that reaction backwards, it's quite simple. I just add water to go backwards. This acyl chloride, this also could react if I add ammonia, NH3, I can get the amide, and if I add an amine, I get the N substituted amide. Okay, there are a few more things to add on. Okay, and these are ones that quite a few of you missed off on your diagram. Firstly, the Grignard's reagents. So I can make a primary alcohol by reacting methanol and adding a halogenoalkane and magnesium. Those two we have to react in situ in dry ether. That makes my Grignard's reagent. Then I can react them with methanol to make my primary alcohol. I can use my aldehydes to make a secondary alcohol. I can use a ketone to make a tertiary alcohol. And I can use carbon dioxide to make carboxylic acid. And if I get it wet, I can basically do the halogenoalkane to an alkane. So these are all Grignards. So I'm just going to put Grig on all of them. That's a Grig. Grignards there as well. Okay. A couple more to go through. Aldehydes and ketones can both react, so make that a bit messy, but they both react to form a hydroxy nitrile, and that's KCN, well, it's actually HCN in the presence of a little bit of KCN. Okay, that then can be turned into a carboxylic acid. This is acid hydrolysis, and we just need dilute acid. You can use dilute hydrochloric or dilute sulfuric there. Okay. Couple more that you possibly haven't come across yet, but I'm just going to add them in to complete it a little bit. Nitrile and amine Nitrile can be turned into an amine using lithium aluminium hydride, LiAlH4 and dry ether. And you can turn your amides, I'm going to have to go around the side a bit because I'm lots of different ways of making a carboxylic acid. I'm running out of room. I can make a carboxylic acid there, and that again is the same, it's hydrolysis, so dilute acid, so any dilute strong acid will work, hydrochloric or sulfuric. Acid chlorides can also make esters. This reaction is not reversible, and all I need there is the alcohol. Okay, so that's the first of the spider diagrams. I haven't put everything on there because I haven't done all the reactions of the amines or the amides or indeed the nitriles. So I've left those ones off for the moment because we haven't covered them so far. But that's all the reactions that you've covered so far in the year, and now you just need to go away and learn it. Okay, so that was the easy part. That was drawing out the spider diagram. Now comes the difficult bit. You've actually got to learn the spider diagram. You've not only got to learn the reagents and conditions, but you've also got to be able to interconvert between the different functional groups. But there are ways of doing this. So one good way is to write out all the functional groups on separate pieces of paper. And that's exactly what I've done here. So on each of these pieces of paper, I have a functional group written out. So you can see there, hopefully they are all different. Okay. Then what you need is a willing volunteer, or maybe an unwilling volunteer, and your spider diagram. You're going to give the spider diagram to your volunteer, who is going to check it, so you can't cheat, and this is what is going to happen. Okay, so I've turned all my pieces of paper face down, so my volunteer is going to choose 2 of them, and they're not going to let me see which 2 they've chosen. They're going to look at them, find them on the spider diagram. Then it helps if you've got a bit of a timer, or you can do this without a timer, it's up to you. But they're going to show me the 2 that I've got to interconvert. So I've got to convert, a nice easy one to start with, because I need to convert a halogenoalkane into a carboxylic acid. And that one's quite straightforward. So I'd say, okay, I'm going to convert my halogenoalkane into my carboxylic acid. I'm going to add sodium hydroxide dissolved in water to make the primary alcohol, and then I'm going to oxidize the primary alcohol to a carboxylic acid using acidified potassium dichromate, and I'm going to heat it under reflux. If I wanted to go the other way, from the carboxylic acid to the halogenoalkane, that's again very straightforward. I would just reduce the carboxylic acid using lithium aluminium hydride and dry ether, and then I would add either PCl5 if I wanted the chloro, sodium bromide in 50% concentrated sulfuric acid if I wanted the bromo, and phosphorus and red phosphorus and iodine if I wanted the iodo. And I'm going to check with my volunteer.
Correct.
Yay! Okay. You ready now?
Yes.
Okay. So my volunteer is going to pick another 2. And around so that you can see them. So I've got an alkane and an N-substituted amine. So I'm going to turn the alkane into the N-substituted amine. This involves quite a lot of steps, if I remember rightly. Right, so I'm going to take my alkane and I'm going to add a halogen in with UV light to turn it into a halogenoalkane. I'm then going to add sodium hydroxide in water to turn it into the alcohol. I'm then going to oxidize the alcohol to a carboxylic acid using potassium dichromate and sulfuric acid and heating it under reflux. I'm then going to turn the carboxylic acid into an acyl chloride using PCl5. I'm then going to add an amine to my acyl chloride to make an N-substituted amide. Okay, so that's just one way that you can learn the reactions of your spider diagram. You can write the spider diagram out many, many times just to get it really cemented into your head so that you know all the reagents, all the conditions, and how you can interconvert between the different functional groups. That's very important as we move forward into the benchmarks in June, and looking further ahead to the exams next year. So until then, take care, stay safe. Speak to you soon. Bye bye.